Good morning, everybody. We'll get started in about 4 minutes or so. Looks like we have everybody piling in now, which is great. So we'll get started as people start coming in and what have you. We won't give the customary 5 minutes because this is a Zoom meeting and not a physical meeting. So just a note as we go through this presentation, I would prefer that you keep questions till the end in terms of audio ones, just because I can't see who's raising their hand or anything like that while I'm presenting, or it's a little bit hard to focus while I'm doing that. But if you do have questions, drop them in the chat as we go, and I'll pick them up as we go, and there'll be time at the end for questions and what have you if you have them as we go through. I think that would make the most sense for this. So to introduce myself, I'm Paul Edman. I work at the Faculty of Arts and Sciences Research Computing. I am your liaison between Center for Astrophysics and Research Computing, which runs supercomputer at Harvard, runs the Cannon cluster. And so I'm a professional astronomer by training. So I've done a bit of this work in terms of magnetic hydrodynamics and what have you. So we're going to be talking today about code optimization. That's kind of where we're going to be working through on this. And if you need any help with Canon specifically or what have you, you can feel free to attend our office hours, which is on Wednesday, or drop us a ticket. We can help you out. But today's topic is on code optimization, is what we're going to be covering today. Kind kind of give you an overview as to where we're going, where I kind of go through the reason why we care about code optimization, why it's important. Then we're going to talk a little bit about CPU architecture, because it actually, in order to really optimize your code, you have to understand what you're optimizing your code for. Then we'll talk a bit about compilers. This is going to be probably the part that's going to be most specific to GCC and Fortran. We're going to try to keep this as high level as we can so that we can cover all the different code bases that people use, ranging from Fortran and C to Python to R to Julia to all the different types of things. It turns out that a lot of the optimization rules you would normally use apply pretty much across the board. They'll go cross language, but for the compiler optimization section, we are going to get into some of the nitty gritties for GCC and the Intel compilers, mainly because they're also useful, because the things that are talked about there will also be useful for other code bases. We'll then talk about general rules regarding this, regarding optimization. Then we'll talk about parallelism. Really what we're trying to get at in this particular conversation is single stream optimization, so you get your code to run as fast as you can, not necessarily the parallelism, although parallelism is going to be a very important part of this. And then talk about next steps, how you go about actually doing the optimization, how you plan this out, because code optimization can take a lot of time depending on how far you want to go with it. So that's kind of the overview of where we're going with the presentation as to what we're going to be covering. So let's start with the justification. Why do we need to do this? Why do we care about code optimization? And the reason we care about code optimization is Moore's Law. Moore's Law is probably the most convenient way of thinking about why optimization is important. So for those of you not familiar with Moore's Law is this idea that was come up back in the 70s by a person, I think is one of the heads at Intel, that came up with this idea. And it's actually a self-fulfilling prophecy. It's not really empirical or really a theoretical thing. He just made this self-fulfilling prophecy saying that Moore made the self-fulfilling prophecy that said the number of transistors you can fit on a chip will double every roughly 2 years or 18 months, depending on how you want to quote that. Industry has actually kept up with that. There's no reason the industry had to keep up with it, but it did. And so basically you could count on, for basically the last almost 50 years, the transistors on a chip would get smaller and smaller and smaller, so you can cram more and more and more on there. That has been breaking down recently, and the main reason why is that we're running into physical size limits of the chip. You can't shrink features on the chip smaller than single atoms, and we're getting down to the point where we're almost getting to that size scale. Since that's a fundamental limit to this, there's a limit to how small you can shrink transistors, and thus a limit to how much power you can pump through. Because the reason why this is important, that this doubling is features is important, is that if you can shrink this lowers the power envelope for the chips, which lowers the amount of heat that the chip generates. Because if you weren't aware of this, a computer chip is almost a perfect greenhouse gas emitter insofar as that you pump a bunch of electricity into it and it converts it directly to heat. And so by doing this, you generate a lot of heat. You got to get rid of it. You got to dump it somewhere. But that's just a limit as to how fast you can run a chip. Is based off of how much heat it puts out, because you can't cool it very quickly, very efficiently. So if you can cram more transistors in there more efficiently, you can run it at a higher clock speed. You can also get a bunch of benefits in terms of additional channels to do work, and that increases computational throughput. Well, since we've gotten to the point where we can't shrink features anymore, that means that chips are at the limit of how fast they can reasonably go. You may notice that if you were to benchmark, like say a Haswell chip that's like 2 generations ago and Cascade Lake, they're actually not that different in terms of speed. The speed actually isn't that different. And that's because we can't shrink the die size anymore. We're running into physical limits in terms of chip architecture. Right? So since we can't rely on the chips just to give us free speed ups, which is what everybody's basically been relying on for the past 50 years, is basically saying, well, I know that within, like, if I wait like a couple of years, I can just buy a new machine, and the new machine will give me basically a factor of 2 speed up, just by fact it's a new machine. That's no longer going to be the case, because the chips that we can design, we're running out of tricks we can pull to do this. Now, somebody may come up with a revolutionary new idea, and this may happen, to then make things just go faster by fiat. But given the current technology that we have, this is kind of what we're running into. So the only way you can really gain speed now, aside from waiting for some sort of crazy breakthrough in terms of architecture, is with code, is to make sure that your code is efficient as possible. And this has been kind of the dirty secret for many years recently, is that people have been kind of lazy in their code writing. Back in the 60s, 70s, 80s, when your chips weren't that fast, you had to really optimize your code. But then through the 90s and the 2000s, you really didn't have to do much work because you get free speed ups just because the chip architecture would change and you would get a speed up just from that. Since we hit this limit, now we have to go back and do the hard work of actually optimizing code, of actually making sure that our code is numerically as efficient as possible so that we can get speed ups. So this is kind of the justification why we need to do this work. So your modern chip architecture looks like this. This is a block diagram from WikiChip. If you ever want to nerd out on what chips look like on the insides, highly recommend WikiChip because it has a bunch of these different details in there and a bunch of different information about what this looks like. But this is your basic CPU architecture in terms of what's going on. And to kind of give you a breakdown of what these different things are, because they are important to know what they are, first, let me step back and kind of give you an idea as to what the chip does when it actually runs. So the first thing that the CPU does when it actually wants to process your data is that it pulls it into a cache layer, which is what we're going to talk about in the next slide. It then uses that cache as a quick way to access data. It pulls the instructions that it's going to run into the instruction cache. It then looks at those instructions, takes a look and says, okay, what do I need to do? Are there any branches in here? This is where you hit the branch predictor. The branch predictor is what looks at an if statement and says, okay, I'm not quite sure which route this branch is going to take, but I think it's probably going to take this one. So I'm going to preload all the instructions for that branch that I think it's going to take. And if it doesn't take that branch, I can just jettison all that work and go grab the other stuff. But if I did guess correctly, I'm going to gain a ton of speed by doing that. By the way, this is where a lot of the problems that we've hit recently within exploits to the chips have come through this branch predictor, because this branch predictor basically executes code that ahead of time that you may not actually want executed and may actually cause a security problem. However, for HPC purposes, the branch predictor is actually really important and really useful because it basically gets you free cycles and basically tries to get ahead of the game in terms of figuring out which branch you're going to go down. Anyway, the processor then fills all the registers, specifically the instruction registers, saying, okay, this is the code I'm going to run, and then I have data that I need to process with this code. Those are the data registers. The data registers have a bunch of different modules attached to them, and there are multiple data registers, so it can run things in parallel. Because if the instruction set is the same for a bunch of data, there's no reason to run that in a serial process. We can run that across all the registers simultaneously, and this is what's known as vectorization. This allows you to be able to run things all at the same time with the same instruction set. This is actually how GPUs are so efficient, is that they basically take these same instructions and you just stream the data across those instructions. You just have a ton of lanes and you just do it. So it's basically somewhat free parallelization. Parallelization you don't have to think about. This is what's called SIMD, single instruction multiple data. This is what you'll see in the architecture. But you'll move down, and the basic unit of work is what's known as a micro op, and that's the CPU cycle. So when a cycle happens, that basic unit of work is what's known as a micro op. Right? And so on this diagram, whenever you see a micro op, that's it. That's a CPU cycle that's having to be done in order to do that operation. And I know it's a little bit small on the screen. You can find a detailed version on WikiChip in case you're looking at it from the nuts and bolts. Right? But all these different units that are added on to these different lanes or different data registers are things that can do math and things that can do different operations. So you have like the ALU, which is the arithmetic logic unit. You have the address generation unit, the AGU, which helps seek out addresses for you, helps you to find different places in logic. You have the multiplier, which does multiplication for you. You have the fuse multiplied add, because it turns out that a lot of times when you're doing math, you do multiplications and adds at the same time. So in order to do that all in one go, which is much faster, the fuse multiply add unit does that all at once, which is actually something you should keep in mind when you're writing code. If you write things in a way that utilizes that fuse multiply add, where you have a multiplication and add at the same time, you can have that in there. The chip will actually use the FMA unit to actually do that math, which is much faster than just doing it individually. Right? You have the integer unit, which does purely integer math, not concerned with anything else but integer math. You have the floating point unit, which does only floating point math and doesn't concern with anything else. You have the LEA, which does loading effective addresses. And then if you need to do encryption and what have you, the AES, the advanced encryption standard, does the encryption stuff specifically. So all these different units on this chip do these different specific things. And so if you can leverage those specific units, you're going to gain a lot of speed by playing within those different units that are there. So if you need to do encryption, the AES is there to do the encryption work for you, and will speed it up just natively on the chip. Intel and AMD put a lot of work into their chips to make sure that they have these type of units on there, and this is just a subsampling of all these units, such that they will pick up on specific workflows, such as like for machine learning and what have you. There are individual units that are added for those purposes to do that sort of work. But this is the basic CPU architecture. So again, just kind of reiterate, it'll go through, pull down things into cache, then it will dump things to instruction register, take a look at those instructions, make some guesses. It will then run those instructions and pull the data through that needs to be run for those instructions. And every time it has to load new instructions, it has to go back to the instruction cache, look at that, and keep on going back and forth. So the name of the game is to not touch the instruction cache, but have it just keep the instruction that's currently working on, but it has to go to the instruction cache and it'll look there. But then to keep data streaming through this as much as possible without changing instructions. Right? And you want your data to be streamed and put together in a way that's conducive to that. So how you handle that data then is in this memory hierarchy. So all your chips are basically built off of this memory hierarchy, which has different penalties for getting access to it. Right? So the arrow on the left is dealing how much latency it takes to get to each of those levels of cache, and the arrow on the right deals with I guess it's your right, my left. So I guess it's on left. So on the left is the latency. The arrow on the right is the size. So the registers are small. Right? The L1 cache is also small but a bit larger, but it takes a penalty to get there. Okay. The L2 cache is even larger. The L3 cache is even larger than that, and basically is adjacent to main memory. Okay. So the goal of the game is to get your stuff down into the lowest cache level you can get to. Okay. So if you can break your work up into small enough chunks that will drop into the caches, you'll get a speed up for this. And this is for the Sandy Bridge architecture. The sizes here that you see are much larger for more modern chips. Sandy Bridge is now about 5-6 years old in terms of a chipset. So like the L2 cache these days is more like 2 megs as opposed to 256K. Okay? So it's a bigger cache now for that. Typically, you're not going to drop into L1 cache. L1 cache is almost impossible to fall into. But level 2 cache, the L2 cache, is something that you can typically fine-tune your code to fit into. And the way you do that is by constraining the data arrays that you have such that they will drop into L2 cache. Working in that array on that size scale, and then having it only do all the math you need to do on that array, then go back up to main memory and pull in the next thing you need to do. Right? L3 cache is usually shared amongst the chips. And usually that's stuff that you'll touch next and is based off of, is basically shared among all the different chips. The L2 cache is specific to the chip you're on, specific to the core that you're working with. Right? The L3 cache is kind of more shared across the board. But you can see here, there's a big, huge penalty to go to main memory. To go out to main memory, it takes forever in terms of cycles. And that creates a major slowdown. But if you can hit any of the cache levels, it's much faster to do that. And so I can't stress this enough. A lot of the a lot of the benefit you'll get for speed up, a lot of things you're looking for when you're doing code optimization is to fall in these cache layers and to drop your cache emission rate. You can get a factor of 10 to 20 speed up just by making sure you're hitting these different cache levels properly. Now, you can't necessarily do that. That's dependent on the compiler to decide that. Okay. So like if you're in like Python or like Julia or any of these different things, or even in Fortran or C, you can't tell it to say, hey, drop into the L2 cache. You can't say, put this thing in the L2 cache. What you can do instead is to make sure that your arrays are sized correctly, that the compiler says, hey, this will fit, and then move that into cache. You're relying on the compiler to do that work for you. You're not going to be able to do that, but you can provide suggestions to the compiler to do that sort of work. And that means right-sizing your arrays and your variables to fit into these different cache layers, such that and then rely on the compiler to actually drop things into the correct places. Okay. So that's the memory hierarchy. This is something that you really should be familiar with in terms of how the different hierarchies matter. And really, you want to try to drop into this L2 cache layer and be aware of how big your arrays are. Right. So let's look at compiler optimization. Let's start actually talking about optimization specifically. And compiler optimization is probably the easiest optimization you can do because it's free. You don't have to change your code. You don't have to do anything. You just have to pick a compiler and pick the flags you want, and it will do the compiler optimization for you. And frankly, a lot of the optimization that you're going to be relying on, a lot of stuff that you want to do is going to be compiler optimization. And if you actually want to see how much compiler optimization is being done, you can set it to no optimization and then turn on, and then start turning on levels of optimization. You'll see how much is done. It's quite astounding, really. So a few things about compiler optimization. First and foremost, use the latest compiler. I can't stress this enough. A lot of people use really old compilers. It's not great because they're not, because there are bugs that appear in previous compilers. There are efficiencies that come in with different techniques for optimization. Using the latest compiler will give you a lot of benefits. So if you can do so, do so. If your code cannot do so, and you don't have control over that code, you should talk with the people who wrote that code and tell them, hey, you guys, you need to upgrade such that you can use a modern compiler. I know some code bases are constrained to using like the system GCC, which is like, if you're using CentOS 7 is GCC 4.8, which at this point is ancient. If you're stuck using the system GCC, that's not good. You want to use the most modern compiler you can get your hands on for your code. Right? Second, you want to make sure that when you're running in production, you remove all your debug flags. This is a common mistake that's made, is that people will just kind of build their code and not recompile the code for production runs and work with debug flags on. That will drag down your code performance substantially. So you want to go through and make sure you remove all those debug flags that are there for when you're actually doing a production run. When you do remove those debug flags, just a caution, test your code to make sure the code results hasn't changed. I've had it be the case before that when I've run code and I've removed the debug flags, the code result changed because the order of our operations changed, or something the debug thing was doing had actually masked a bug in my code. It actually turns out that debug stuff can actually mask actual bugs. This has happened to me before. So when you turn off debugging, always be sure to test that your code is producing the correct results after you turn off the debugging stuff, because sometimes the results will change and it will catch you off by surprise. You'll be like, what the heck happened? And the reason before that is because the debugging was creating a different code path than what you would normally run. So just be aware of that. You want to test your code performance for different optimization levels. As we're going to point out, there are actually 4 different optimization levels you can be in. Each of those have different benefits. And sometimes moving to a higher optimization level may actually give you no benefit. You, as the 5th bullet point points there, you only want the optimizations that improve code performance. Sometimes going to a higher optimization level will actually create code bloat and actually create problems. So you want the lowest number of optimizations possible for compiler optimizations. You want to pick the right level. You just don't want to go all the way to the top optimization level. Okay? There are benefits to and penalties for each level, different things going on, so you want to be aware of that. Test your code performance at different optimizations levels as well. You should have a very well characterized code such that you will say like you start at the lowest level and you test it there, and then you top it to the highest level, and you should see how your performance changes as you change that level. So you can see what are beneficial optimizations and which ones aren't beneficial optimizations. You always want to verify your result is correct. It's still what you expect when you change compiler or optimization level. Compilers make different assumptions about math. They make different assumptions based on optimization levels. The compiler may in fact have fixed a previous bug that you were relying on for your code to work properly. I've seen this happen as well. And therefore, it's actually a bug in your code that you need to fix that was relying on a bug in the compiler that was operating in a way that you didn't expect, or it's not a bug in the compiler. The compiler just changed the way it was handling a thing, and that made your code operate differently than before. So you always want to check your code result is still the same and what you expect it to be. Or if it changed, it didn't change substantially, because maybe like round off changed or something like that, and you really care about your round off error. What you really care about is the details of the bulk result. Okay. Another thing I'll stress is that you want to read the manual page for your compiler, as compilers vary depending on how they execute the optimization level. So optimization levels will change from compiler to compiler. They have different options in them. They have different ways of handling that. The manual page for a compiler, which is just, if you want to get access on that, you just do man, M-A-N, space, and then the compiler you're going to run for GCC and for Fortran. It'll just print out the manual page and you'll be able to read through that and see what's going on, or you can find manual pages online and read through that. Again, wealth of information there. They're very complete, also very opaque and arcane. So be ready for that. It may get a little bit weird in there. Just deal with it and move through it because there's a lot of good detail that's in there. So let's talk about the different levels of optimization. So the first level of optimization is -O0. That's an O followed by a 0. It's kind of obnoxious that they picked a capital O, but that's what you got to deal with. So it's capital -O0. This disables all optimizations. So this is basically, you have no optimizations on. This is just running the code as it is, as it sees it. This is good for debugging, but should never be used in production. If you're in production mode, you never want to be on O0. Just don't do it. If you want to truly see how much work, though, your compiler is doing, try out O0. Try running your code as O0, and your code will run crazy slow. I can guarantee this. I've done this before. It's kind of fun to watch because you'll see the marked difference between this level of optimization and just the next level up, the O1. It's about a factor of 10 to 100 in terms of speed. So you can see how much work your compiler is doing for optimization. It does a lot of work. By the way, O0 is the default optimization level for GCC. So you never want to run GCC without specifying an optimization level, because otherwise it will just throw in this as what it is, and it's going to run dead slow. So just be aware of that for GCC if you're using it. O1 is the next level up, and what O1 does is that enables optimizations for speed, but it disables optimizations that impact code size, such as intrinsic inlining. So what intrinsic inlining does is that it takes like say cosine or sine, which is a math function. What will happen at higher levels of optimization is that we'll take that math function and actually inline it into the code rather than having it to go all the way back to the compiler to pull that library out. Like say, okay, I'll just take this library, this function, just put it in the line, as opposed to having me have to call this function to grab it. Okay? O1 does not do that inlining. It just says, okay, we're just going to take some optimization for speed. This optimization level is safe in all cases. Namely, the result you get in O0 is the result you're going to get in O1. Okay? The result will not change on O1. It will still be the same. It is safe in every single case. Okay? So there won't be any weird out of order things happening. Everything will happen the way that you expect it to happen. O1 should be considered the absolute minimum optimization and should not be the norm you use. If you have to use it for the sake of code consistency, do it. But if not, you should probably never use O1 as an optimization level unless you absolutely have to. Right? So that's O1. O2 is the default optimization level for Intel. And O2 is considered safe in most cases. Okay? It can lead to some variance in round-off error or out of order of instruction in edge cases, but in general, it's safe. It won't create anything weird or crazy. I have seen it that O2 will change results if you have bugs in your code or something weird going on, or if your code's super sensitive to order of operation. So you can see some weirdness from O2, but typically that's not the case. At O2 level, in Intel, vectorization starts happening. And that's that thing I was talking about before, where instructions, if there is an instruction set that can be applied to a bunch of data, it'll say, okay, I'm just going to apply this all at once to this data, and it'll start vectorizing your loops, which is very good. You want to have vectorization. If you want to turn on your vectorization report, which is important to see what is vectorizing on and seeing like, oh, I want this loop vectorized because it has a bunch of work in it. The report's very important for figuring that out. And we'll talk a little bit more about vectorization a little bit later. You have inlining of intrinsics, which I talked about before, which is basically things like the exponentials or cosines or sines or things like that. Native math functions and what have you will get inlined in this, which is good because that way you don't have to do it. That's an additional function call that's not needed anymore. And it'll be able to actually vectorize those intrinsics as well. Intra-file procedural optimization is also allowed. Namely, what will happen is that if you have a bunch of functions in a single file, like so you have your code, you have a bunch of functions and subroutines in that file, it will take and start looking between those functions and say, can I inline these? Can I take these and run optimizations on those functions such that I know if I put this function here, and it's in a bunch of other functions within this, I can do some optimization work there. Okay. This is not inter-file, so it's not looking between files. If you have a bunch of different C files or a bunch of different Fortran files, something like that, it's not going to look between those files. It's only going to look inside of the file itself. Okay. Loop unrolling will happen. Namely, if you have a very short loop that say it's like only has like 3 indices or something like that, it'll say, okay, rather than having this, having it loop over that, I'm just going to copy this 3 times and unroll that loop. Okay? It won't unroll large loops, but loop unrolling can be very, very effective for short loops because that it's easier for it to actually just replicate that code multiple times than it is to just run the loop itself. It's more efficient for the compiler to do that, and also can find intra-loop optimizations as well. It may also rename variables. So a variable that has a ridiculous name, it may just decide to rename it such that it's more effective. It doesn't really matter for you because frankly, all that matters is that for what the chip sees. Right? Variables may also be simplified at this point. So it may say, oh, I see this variable that you have. I'm going to actually change it such that it looks like this, so it's simpler than it was than you had it. So that way it's more obvious as to what's going on. Intel compiler specific, codes compiled with O2 may also start picking up additional Intel chip specific optimizations. This is something that you should be aware of with the Intel compiler. The Intel compiler works on all different chipsets to be sure, but it does have a lot of tuning for specifically Intel chipset. And so you will get benefits for that. There's also some rumors going around, confirmed or not. You take it with a grain of salt. The Intel compiler may throw in some stuff to slow things down the AMD chipsets. I personally have not seen that from my own experience, but other people have. So if you're using an AMD chip, the Intel compiler may in fact run slower than GCC and may in fact not be the optimal thing to use. So just be aware of that sort of thing. Definitely if you're on an Intel chip though, the Intel compiler invariably is probably going to be faster than GCC. Right? The last level of optimization is the O3 level of optimization. O3 does everything O2 does, but includes more aggressive optimizations. And these include aggressive loop transformations. They may in fact fuse loops together. So if you had 2 loops that are next to each other, they're iterating over an array, and they're actually separate loops, O3 may in fact decide to fuse them together as to keep them apart. Now, you may not want that because that may break the order of operations. That may in fact create math weirdness that you may not actually want. On the other hand, it may have in fact be something you do want, you just didn't think about it, and it'll fuse it together. Another one may be a block, unroll, and jam, which basically, as you may suspect, what it does is basically it takes a loop, unrolls it, and then unrolls another loop and jams those two loops together. Okay. That can create speedups, but also can create weird out of order things that you didn't expect. If statements may also get collapsed. If it says, oh, this if statement is redundant, it may say, okay, I'm just going to get rid of it, because if statements are expensive, and the less if statements you do, the better. Arithmetic reordering may happen as well. So your math, which may be in a specific order, may get reordered because it's more efficient that way. Right? Similarly, less rigorous but faster methods for math may take place at O3. So it may say, well, I could do this more rigorous thing, but I could do this other thing that's much faster, but the round off error is worse. And so the round off will change and the metical will change slightly. But I'll do it anyway because I don't really care about that. I just want speed. What this means then is that also at O3, I should mention, GCC has the automatic vectorization starts happening for GCC as well. You can always force vectorization to happen by including these flags. And frankly, any of these things I've been talking about here, you can force them to happen by including specific flags as well. O3, O2, O1 are just kind of an assembling of a bunch of different flags all under one bucket, if you will. Unlike O2, which is generally safe and may not change your results, O3 is the kitchen sink approach. It's throwing in everything it possibly can do. Therefore, O3 can lead to code bloat. Code 3 can in fact slow down your code because it may do things that it didn't expect. It may actually be inefficient in doing that because it's making a bunch of guesses that may actually not be true. But O3 may also massively speed up your code. So it's kind of a crapshoot as to whether or not you'll end up with a faster code or a slower code with O3. So your mileage may vary on that one. But your result may also change as well and change substantially. Therefore, with O3, you definitely want to test and verify your code. You should do this with any level of optimization regardless, but with definitely O3, verify your code results the same or it hasn't changed substantially. Okay? Because O3 may do something a little bit funky to you. If you can get O3 to work properly, it can be crazy fast. But it may also do all sorts of weird things. One additional thing that you should be aware of is the dash fast option. Dash fast is basically O3 plus architecture specific optimizations. So it's basically throw in everything. If you throw in dash fast, it's going to do everything it possibly can. Okay? I don't usually recommend dash fast just because it can do weird things that you're not expecting. And also the processor specific optimizations can create problems, which I'm going to talk about next. So additional things that you should be aware of and notes about compilers before we start talking about more general things. Each compiler has a wealth of options and differences, so it's worth your time looking at them, especially what options are being applied for O1 through O3. One option I didn't mention in this, but should be one is interprocedural optimization is IPO. You'll see it as a flag. This is for optimizing between files. So if you have your code broken up into files, dash IPO will optimize between those files as opposed to what was being done before, which is internal to that file itself. Dash X host, dash AX, dash march. These all can be useful for chip-specific optimizations. What we've been talking about before are generic optimizations that aren't specific to the chip itself. What dash X host or these other options do, though, is make your code not portable. What it'll do is it'll say, okay, for this specific host that I am on right now, optimize for this chipset. Okay? This takes any of the guesswork out about what you need to have on, but the downside is that you will build for that specific chipset, which means that your code's not portable anymore. So like if you're on Canon and you run dash X host on the login node, you'll get optimizations for that specific login node, but that login node chip is not the same chip as what you have on the cluster itself. Okay? So your code may in fact not even run on the cluster if you built it on the login node. What you want to do instead is that you want to start up an interactive session on one of the compute nodes that you're going to be running on, and then run just -x host, and it'll optimize specifically for that. In addition, if you use -x host, you won't be able to run, like, say, in serial requeue or any of the backfill partitions, because those run on a variety of different hardwares, as opposed to something on a specific hardware. You'll be constrained to the non-backfill partitions for if you run on -x host. So just be aware of that. You can get some nice speed ups though from -x host. It can give you some nice stuff. That said, you can also, if you want to make your code more generally applicable and get the same benefits as -x host, you can go in and pull out what the specific optimizations that it was going to apply for that specific chipset and put them in a non-host specific way. Once you do that, your code is generic and it will pick up whatever optimizations it can happen to run, whatever chip it's on. So just be aware of that. As to which compiler to use, Intel, GCC, or something else, generally, most compilers are the same. You can get GCC to run the same speed as Intel for the most part if you pick the right options. Same with PGI. I haven't mentioned that, but the PGI compiler will run just as fast as GCC and Intel. Some compilers, though, have been built very specifically and will work really well. The Cray compiler is known to be superior in most cases, but is only available on Cray machines. So if you have access to a Cray and have access to the Cray compiler, use that preferentially over GCC and Intel. If you can, use it. They put a lot of work in there. Their compiler group is really excellent. They do a lot of good work on that. Generally, from my own experience, the Intel compiler works best out of the box. So if you just want a compiler that's just going to work and work well, Intel is the way you want to go. GCC tends to include a bunch of stuff, options as default that drag down code performance. As you saw, GCC runs at -0 as its default, which is kind of crazy. It also has a bunch of debug flags turned on by default as there, which is not great. So you want to make sure that if you're especially running GCC, you include the correct options. If you're running Intel, you can just run Intel out of the box and it'll work fine. It makes usually pretty reasonable assumptions just right out of the box. Okay. So let's talk about general optimization rules. Right, so this is now, we're getting out of the land of just specific Fortran and C sort of stuff, that's specific GCC and Intel compilers. Now we're talking just generically. Okay. Number one rule, use the latest compilers and libraries. Guarantee that. So if you're using like Julia, Python, R, any of those things, use the latest. Same with the libraries, use the latest. If you can, find them, do that. Likewise, if you can build R, Julia, Python using the latest version of GCC and or Intel or something like that, do that. Okay, any of those higher level languages, you can always build against a lower level compiler, okay? And use a faster compiler for that, and include optimizations in that when it builds it, so that you then get the benefits of those. Okay? A lot of the libraries for Julia and for Python and what have you already have a lot of those options included, especially if they're relying on GCC and what have you. But if you really want to get the most out of your code with that, definitely build like yourself a curated version of that. Okay? If you're really looking to get like every single second out of your code. Okay? The versions that we build on the cluster are all generic. The reason why is because we just don't have time to build specific optimizations, but any of the modules that we build in the cluster of the stuff that we build can be built specifically by you as well. You can always build that yourself. So if you really want to get into the nitty gritty, you can always build your own version of Python, your own version of R, your own version of Julia, and rely on that as opposed to the ones that we build. And especially if you want to get the most out of it, do it that way. Second, leave yourself informative comments in your code. This may seem like a minor thing, but it's actually not. Comments are free. It doesn't lead to code bloat. The compiler will ignore them, but they will make it a lot easier for you to go back and figure out what exactly you were thinking when you wrote that section of code. It will also help other people later on down the path look at that point of code and say, oh, what was this thing they were trying to do? Oh, here's a better way of doing it. Okay? So comment your code properly. Right? Third, make sure your loops are ordered appropriately for your arrays. As you may or may not be aware, for Fortran, the fastest array index is the inner index. Okay? For C, the fastest array index is the outer one, okay? Which is not what you expect. I'm not aware of what it is necessarily for Python or for Julia, but you get the idea. you want to make sure that you have that you know which loop is ordered properly, and then iterate over that faster loop, whatever that index is going to be. Okay, so and that will give you a pretty good speed up if you do that properly. So be sure that you're ordering your loops properly. Avoid if statements buried in loops. Okay, I actually ran into this myself when I was writing code, and I had a code where I wrote a bunch of if statements inside of a loop to dump data. Instead, what I did was that I broke those. I basically copied the loops inside of the if statements. I moved the if statements outside of those loops, and then so it only evaluated the if statement once, and then ran the loop inside of that. Right. So if you can move the if statement outside of the loop, that's what you want to do, because every time it hits an if statement, it's going to be additional cycles that it takes to do that. If statements are expensive to run, so you want to cut those down as much as you possibly can. If you think of different ways logically to come up with the same if statement or avoid them completely, do so. Okay. You want to use temporary variables to hold things, hold math constants such as pi. So if you have like a common math constant you're going to use all the time, like say like 4/3 is something like, let's say 4 pi over 3 is like something you're just going to use constantly. Make a constant that is that, rather than just having that math in the line. Okay, you'll save yourself a lot of headache by doing that. It'll save yourself a lot of time, computational time. Okay? Similarly with divisions and exponentials, if you can avoid a division and instead turn that into a multiplication, say you have like say you have 1/2. Okay? Rather than writing 1/2 in your code, write 0.5 and then do the multiplication through. Okay? Or for an exponential, have that already evaluated once and don't evaluate it again. Because exponentials and divisions are expensive to do. Same with anything that's going to call like sine or cosine or things like that. You want to do those once if you can, once and only once within the loop, or outside of the loop once if it's something that's going to be a constant, something that's not going to vary. Okay? If you have to do it, do it, but if you can avoid it, avoid it. Okay? So divisions especially, if you can make an array that evaluates a division beforehand. So let's say you have an array that you have to divide across the board. Do that once across the board and have that be another variable that you've made that is that division. Okay? And then you have two arrays, one that's the array that you need and one that's the divided array. And you just use the divided array when you need it, as opposed to just having to do that division all the time. Okay? Another one that's actually a lot more subtle, and one that actually surprised me, because coming from the CFD background, coming from magnetohydrodynamics, this is not something you expect to do. But for machine learning, this is critical, is setting the variables to the right precision and size. Okay? For computational fluid dynamics, you know that you want to run in double precision, otherwise your result gets weird. Okay? However, for machine learning, running in double precision doesn't actually gain you anything. It actually it actually drags down code performance. Instead, you may want to go to single precision, or you may want to do integer math as opposed to doing double precision math, and you'll still get the same result, but you'll be running in a faster way. Because running at higher precision creates penalties to run. So you want to run at the lowest precision you can get away with. Okay? So don't just throw the kitchen sink of double precision at things, okay, which is what I natively have the expectation to do as a CFD guy. Instead, go to our lower precision, and you may get a lot of benefits out of doing that, especially if you can go between like integer math and floating point math. Okay? Because integer math in many cases can actually be faster than floating point math can be. Okay? And this is especially true for machine learning algorithms. Okay? So look at lowering your precision, because that can gain you some good performance. Use timing statements, print statements, or a profiler to find your hotspots. You don't want to waste a ton of time optimizing a section of code that actually is not the place where your code is spending a lot of time. Okay? You could say, okay, I'm gonna be in this section of code and work on it like crazy on it, but your code was only spending like maybe like 1% of its time there. You want to go for the big ones, not for the other ones. Do not underestimate the usefulness of writing just simple print statements. This is actually a very easy way of just figuring out where things are spending a lot of time. If you want to do something more formal, you can use the compiler itself to do optimization, to look for places where you want to spend some time. Or you can use things like vtune or tau or total view to do some work on that. If you're curious to learn how to use tau or vtune or anything like that, you can feel free to contact us at Research Computing. We'd help you figure out how to do that. Right? But these are ways that can help you isolate hotspots. But if you don't want to go through that work, simple print statements with timing in it will do the exact same sort of work for you. Okay? Just not as much detail, but it'll give you a lot of what you need. If you have a heavy arithmetic section, a section that's just a bunch of math inside of a loop, consider using temporary arrays for data that you're manipulating. So copy all the data you're going to be manipulating within that loop into a temporary array at the beginning. Okay? Do all the math on those temporary arrays, and then copy that data back to the larger array you were using for storing. Okay? That will allow you to drop into level L2 cache just because you've done that. Okay, so using small temporary arrays is a way that you can get into L2 cache. Okay, because all you've done the work for it by implying, okay, I'm going to take this larger array, take the subsection of it, do a ton of math on that, and then copy it back. Okay? You want to lower your cache miss rate and operate in L2 cache as much as possible. Okay? And if you want to get ideas as to your cache miss rate, again, vtune, tau, total view will give you reports as to that. Automatic vectorization is probably one of the, aside from dropping into cache, it's probably one of the biggest secrets to getting your code running fast. Because this way, your code will vectorize and it'll be able to use that SIMD, that native parallelization that's inside the chip itself. Right? So this is where you want to look at your optimization report and see if it worked as expected, that the loops you expected to vectorize will vectorize. Also, you want to make sure your loops are fat. As my friend Cray says, you want to make sure you have as much math crammed into that loop as possible, because that will make it easier to vectorize and you'll get much more benefit from your vectorization. There are hitches to vectorization as to what can be vectorized and not vectorized. The Intel, and there's a lot of details to that I'm not going to cover here. It's an entire talk to talk about vectorization. Intel has a really nice page on vectorization that you should read if you're interested in vectorization. It has to deal with the way you order math and loops and how you handle different things. Highly recommend reading through that if you're interested in doing vectorization work, because it will give you a major benefit by getting vectorization to go. If you can get it to go, do it. Be aware of the first touch rule for memory allocation. Okay? So if you have control over your memory allocation, you want to allocate arrays and variables you will use frequently a lot first. And this is the reason why is that when you allocate memory, the first allocation is the nearest to the chip. Right? And it takes time to get to stuff that's farther away in memory space. Okay? So the first stuff you touch is the stuff that's closest to you. And the compiler assumes that stuff you touch first is stuff that will need to be close by for you to use frequently. Okay? So if you can order your allocation of memory, allocate arrays that you're going to use a lot first. In addition, you want to cut down your memory footprint as much as you possibly can. Okay? So remove extraneous temporary arrays and variables as much as you can. Use temporary arrays when you need to. Don't just get rid of them wholesale, because you will get speedups for that. But there are a lot of cases where you may have a ton of additional memory that you're using for temporary arrays that if you rework the math slightly, you don't need them. Right? And those temporary arrays create bloat in your code, also make it harder to get to other places in the code because it has to scan through those to get to different things. Right? So you want to make sure that your memory footprint is as tight as you possibly can. Right? You want to avoid over abstraction. So don't do pointers to pointers to pointers to pointers to pointers, because it's hard to optimize those, because it leaves the compiler guessing. The compiler doesn't know where it's going anymore. Okay. So don't abstract to a ridiculous degree. Be specific, okay, and well-defined. Okay. Amorphous employee structure code is hard to optimize. So the more detailed, the more specific you can be about variables. So like if you can take a variable and declare it at the beginning, as opposed to just declaring it inline, do that. Okay? Because then the compiler doesn't have to guess as to what's going on. Okay? Be up on the latest numerical methods and libraries for your discipline, and pick the one that is right for your code. Okay? And that may not be the one that's most popular or cutting edge. Okay? It may in fact be one that was written years ago. Okay? Somebody's well-optimized code that was written years ago may actually work better than something that's written more recently because they got too cute. They tried to do something more fancy, right? It actually may turn out that the brute force approach may actually be faster than the nuanced approach. Okay? So be up on those sorts of things. If you don't want to be, if you don't want to write your own stuff, I highly recommend using libraries, just because you rely on somebody else to do that work for you, and you can get some very highly optimized code that way. And in summary, when all else fails, use Fortran with a good compiler. You're not going to beat Fortran with a good compiler. Just bare fact. It's just not going to be the case. So if you can do that, do it. If you can't, then don't. Okay. Let's talk a little bit about parallelism, just because it's kind of the elephant in the room a little bit, because it's like, hey, Paul, you've been talking a lot about these different optimization levels, but I can also get stuff for free by parallelizing, and that's true. Parallelism, the single stream will only get you so far. Eventually, you're going to have to start parallelizing your code. Right? And there's kind of 3 different levels of parallelization. There's SIMD, which is a single instruction, multiple data. That's vectorization. That's what I've been talking about basically for the past almost hour now. Thread-based parallelism, which is shared parallelism, which is what you get from OpenMP, OpenACC, and CUDA. Basically, you have a node, you're constrained to that node, and you're pulling data in from that node, and you have a bunch of threads that are operating over that. And that's an entire talk to itself. I'm going to just mention that it exists and move on. Okay? Thread-based parallelism, though, is probably the easiest next level of parallelism to go. So if you want easy levels of parallelism, SIMD is probably the easiest, followed by thread, followed by the rank, which is MPI, message passing interface. And this is where you start branching out to all the different nodes on the cluster. This is where you start getting to really large scale computation. And for things like fluid dynamics and what have you, you're probably going to have to go all the way to MPI to get things done. Okay? The hybrid approach is also something you should be aware of. This is where you use thread-based parallelism with rank-based parallelism at the same time. This can be really powerful if you want to go to the largest computers in the world. So if you want to go up to things like at TAC or at one of the national labs, something like that, you're probably going to end up having to go to a hybrid approach eventually. Okay. But parallelism is an entirely different talk right here, but this is you should be aware of, especially if you're going to think about restructuring your code. So finally, I want to talk about kind of next steps in terms of what a cost-benefit analysis as to which way you want to go with optimizing your code. Because there's kind of 2 basic methods with code optimization. The first is code improvement, where you just take the current code base you have, scrutinize it. Let's say, oh, this loop is kind of, I shouldn't even do this loop. I should do this instead. Okay? Or say, oh, this if statement here, I'm going to move this elsewhere. I'm going to do that and make that change. Or say, I'm going to change my compiler and make some tweaks, and it's going to be better. Okay? So that's the first method. The second method is to say, screw it, burn it all to the ground. I'm going to overhaul my code completely from scratch. Okay, and I'm just going to start from scratch and go from there. Okay, each has their advantages and disadvantages. Okay, so here are your advantages and disadvantages for code overhaul versus code improvement. Okay, so if you're code improvement, the advantages are that your code, especially if it's an old code or something like that, may have a ton of low-hanging fruit. You may already have a bunch of stuff that's pretty obvious to optimize, and you say, oh, I can just do this and be good. It's fast. You can do this code improvement. May take you like maybe a week to do, and you can find a bunch of things that you say, oh, here's a bunch of stuff I shouldn't be doing. Let me reorder this, or let me do some changes around, some tweaks. Let's do that. It also involves minimal changes, so it's the least amount of work to do. The disadvantage of doing a code improvement is that you can't deal with structural issues. So your code structure, you can't really overhaul your code structure by just kind of doing this sort of approach. It's just not a thing. Second, it's whack-a-mole. So you may hit one thing and another thing may pop up like, oh, I should make this, which leads to the cascade of changes. So you may say, okay, well, I changed this one thing, but by pulling that string, I now unravel this other thing that I need to fix as well. Oh, I have this other thing I need to fix, and this other thing I need to fix. And eventually you're ending up overhauling the code anyway. Another thing is that it can create spaghetti code that is disjointed and unreadable. Okay, so your code readability may get crazy. You may introduce a bunch of bugs by doing this. So code improvement can be really useful from just a very baseline approach, but it has its limitations. And so just be aware of that if you decide to go into to doing code improvement. Definitely, I recommend just sitting down for like a couple of days with your code and just taking and reading through it and seeing if there's anything obvious to do, or messing around with compilers for a while. Okay. Those are easy things you can do, don't take a lot of time, and won't eat up your schedule for doing that. The better and more extensive thing you can do is the code overhaul. This you can deal with real structural issues. You can also completely change which code you're using. So you go, say, from like, if you're using MATLAB, you say, okay, well, I can go to Python or to like Julia, or I can go all the way like to Fortran or something, as opposed to doing with these other things. So I can completely change how I'm doing things. I can also introduce parallelism. So if I want to say, hey, I want to introduce MPI or threads, I can do this by changing the structure of my code completely. Okay. It allows you to say, hey, I have this numerical method I've been using for years for doing this type of dynamics, but I know that my colleague over here has written this completely new method that should be way better. I can now introduce this as opposed to using the old method I've been using for years. Okay. It allows you to take a more cohesive, holistic look at the code and say, okay, let me reevaluate this entire thing. Disadvantage of this overhaul work, I'll tell you up front, takes typically 6 months to a year to complete, depending on how complex your code is. A complete overhaul of your code is going to eat up a lot of time, and it's going to basically be your entire job for up to a year to do. Second, you can get stuck in never-ending code development. I've seen this happen with the project I'm a part of, where they've been overhauling the code for the last 10 years, and it's keeping on overhauling it without actually going into production with it. Why? Because new numerical techniques keep on coming in. It's never good enough. Okay? As the old maxim goes, never let the perfect be the enemy of the good. Okay? You want to have good enough. You don't need perfect. Okay? You need it to be good enough for what your purposes are. Okay? So you never want to be stuck in the code development forever, because you actually have science you want to get done. Unless your entire job is to write code, you want to actually get to actually doing some nice simulation work or processing data, what have you. Doing this work also requires you to have a fundamental knowledge of numerical methods, its code, and the inner workings of the code and everything. So it's really a great way of learning a ton of stuff to overhaul your code. You will learn a ton about numerical methods, a ton about a lot of great stuff. So I can't recommend it enough as a great method for your code, but it will require you to know a lot about your code base. It will allow you to require you to know a lot about modern chips, a lot about how modern stuff is done in terms of how you do optimization work and everything. So just be aware of that. You'll learn a ton though. I had a colleague when I was in grad school who took and did this work actually on their code base, and he did it basically as a learning experience. He overhauled our entire code base, and we gained our code was by being overhauled, allowed it to scale perfectly in parallel. It allowed it to be a lot more efficient. We got a lot of benefits out of doing this work. Saved us probably about 10 years worth of computational work to do that overhaul. Right? So you can get massive advantage of that, allow your code to scale up to a much higher level and do a lot of stuff, but it takes time. It's probably the most difficult part of this entire thing, is to do this overhaul work, but it can be very beneficial. So as a cost benefit analysis, your mileage may vary. So in terms of next steps for you, because this is just, again, an intro, an overview, kind of a survey of what this entire thing is. There's a lot of depth, as you can see. Man pages are your friend. Definitely use them. This Intro to HPC book that I'm linking here is definitely worth reading. It's about several hundred pages of work to go through. Definitely worth your read. Numerical Methods for Scientists and Engineers is a classic of different numerical methods, worth your read as well. Investigating different code libraries is also worth your time, because you may find something that's newer that may be worth using, or something that may save you a bunch of time as well. As always, and Research Computing are here for you. So we do consulting work. We won't be able to rewrite your code for you, at least within the consulting envelope, but we can sit down with you and talk about your code, take a look at things, make suggestions as to different things that are there. Or if you do want us to rewrite your code for you, we have this research software engineering services that we have spun up that you can actually, if you have grant money that you want to throw our way, you can hire us out to do this work for you. and we will do the hard work for you, that you can that you don't have to do this stuff. So if you're interested in that, go to the link there. You can contact us. And Mahmoud is in charge of that work. Mahmoud Shad, he's our guy who's in charge of that. He will be delighted to hear from you, and he will help you. He will help you do a lot of that work and help you figure out what's best for you on that. And at this point, if you have any questions, I am happy to take them. You can feel free to unmute yourself and ask, or you can ask in chat. Do that. It looks like Sylvain has dumped a ton of comments in there, which I highly recommend if you read those, because Sylvain has a bunch of, actually send it to me privately, not to the group. So I will drop this into the group chat so that you can see what this is, what he has to say. So this is from Sylvain. Some good suggestions that you should be aware of. But are there any questions that people have about this? Or, like I said, drop it into the chat, but I'm happy to answer. Also, we have our weekly office hours on Wednesdays from between noon and 3, which you can drop in and chat with us as well. But any questions? Right. Seeing none, I hope you will enjoy your day. I hope this was useful for you. And thanks for attending.